This is problem 41 of chapter 17 on Giancoli 6th edition. So we have one capacitor, so I'm going to try to draw my capacitor here. So two parallel plates. And this capacitor, I'll call it the capacitor C1, has a certain capacitance. It's given to us 2.50 microfarad, and it's charged to this potential difference 857 volts. Now, how is it charged to this potential difference? Well, of course, we have here a battery with that same potential difference. Okay? And we have another capacitor. Oh, but before we talk about the other capacitor, well, since they give us the capacitance and the potential difference, I know that we can also get the charge for this capacitor 1. The charge is just CV. So I also have the charge. And we have another capacitor. I'll draw it down below here. This other capacitor, this capacitor 2, has a bigger capacitance. So to make it clear, it has a bigger capacitor, make it the plates bigger. Now, if the area is bigger, it can receive more charge. So this other capacitor has a bigger capacitance, and this is given to us. It is 6.8 microfarad, and the potential difference that is established is 652. Well, because we have this battery connected to these plates, and the voltage of this battery is 652. So with this charge, with this capacitance, with this potential difference, we can also find the total charge of this capacitor 2, C2 V2. Very well. So there we are. Now what we are going to do is we are going to disconnect the capacitors. They are already charged. We are going to disconnect them from the batteries. So there is no more battery here. The potential difference is still the same. It was established by the battery. But, and these two capacitors are still charged. So I'm going to draw here just to indicate that they are charged. After that, after removing the battery, what we are going to do now, we are going to connect the positive plates, and we are going to connect the negative plate. So let me try to make a drawing here. This plate here is now connected with the bigger plate. Okay? And the negative plate, also the same thing. Okay? Connected with the bigger one. So this is the new scenario now. And the question now comes, what will be the potential difference across each one of these capacitors, and what will be the charge on each one of these capacitors? So the question is, what is going to be Q1 and V1, and what is Q2 and V2? Okay. All right. Comparing the initial scenario, so I'm going to call this INI here, so we remember that this was the initial scenario. Comparing this initial scenario with this final one, I'm putting F here to remind us that we are talking about the final. What is constant? Remember what we are saying. Now, to solve these kind of problems, let's always try to remember what is constant, what is equal before and after. And if you think a little bit, the only thing that is really constant before and after, no, something that we can say for sure, is the total amount of charge. The total amount of charge initially is what? The total amount of charge, I'll put total here, initially is Q1 plus Q2. What is the new total amount of charge? Does it change? Of course not. There is no place for this charge to escape. So this final total amount of charge is equal to the initial. This is a constant. And what is this final? Well, Q1F plus Q2F. But what changes in this scenario? Well, once I connect the plates, these charges are free to move, so they will redistribute themselves. Okay, so that's the only thing that will happen. The charges cannot disappear, they cannot be created. Now we have no batteries anymore, but they will redistribute. Okay, so even though the total initial and the total final are the same, the charge that I will find in each capacitor may now be not exactly the same as initially because they redistribute themselves. Okay, so this is the key to solve this problem. Okay, so the key to solve the problem is, let's write again, the total initial charge has to be equal to the total final charge. The total initial is Q1 initial plus Q2 initial. Do we have these values? Yes, because we have C1 and we have V1 and we have C2 and we have V2. Okay, so let me call V1 ini, V2 ini, to remember that this is for the initial case. Now, should I write C1 ini and C2 ini? Remember that C is the capacitance. The capacitance only depends on the areas, depends on the distance between the plates. These things have not changed. Okay, we still have the same medium between these two plates, we still have the same areas of the capacitors, and we still have the same distance between them. Okay, so C1 and C2 before and after, they are the same. So I'm not even going to bother putting ini for the capacitance. Okay, now let's go. This total charge initial will be equal to the total charge at the end, so Q1 final plus Q2 final. This total amount is the same, but these charges may have redistributed themselves. They will look for better redistribution so they are not too close to each other. Remember, electrons don't like to get too close together. Okay, so let me write now this right side. I should write C1 because, as we said, the capacitance does not change. I still have the same area, I still have the same material between the plates, I still have the same separation between the plates. For the capacitor, 1 is still the same. And then comes the question, what should I write for the potential difference afterwards? So I'm going to write for the moment just V1 final, and here C2 V2 final. This is the equation that I have to solve. But let's think a little bit. When I put these two capacitors together, basically what I have now is a single plate here and another equal plate there. So I created now a new capacitor that has bigger area. Now the area of this new capacitor will be the initial area, the area of this little one here, plus the area of the bigger one. So I have now a new capacitor with this area. And what is the potential difference? I don't know what the potential difference is, but for sure the potential difference is the same for this whole thing. Now this whole capacitor is a single one. So this whole capacitor, anywhere between these two plates, I have the same potential difference. Okay, so that's the crucial thing. Once I united these capacitors, I have now a new capacitor with bigger area. And this new capacitor, the charges cannot change. They redistribute themselves, and the potential difference has to be the same between any point of these two plates. Okay, so the key to solve this problem is this. Now I have here C1 V1 initial plus C2 V2 initial. All these I know. And at the end I have C1 V, C2 V. Okay, this potential difference, V1F is equal to V2F, which is equal to V, a single V, because now I have a single capacitor. And you can see that this whole thing here is equal to CV, where this new capacitance is the C1 plus C2, and this is the new potential difference established. Okay, so that's the idea of this problem. Now we have all the information to solve. What we want to find is the potential difference. The potential difference is the same. Now this whole two capacitors became a single capacitor. Okay? So this equation, from this equation, you can find this V. This V is the same for both capacitors because they are united in a single capacitor. You can still find the charge for the final charge in the that is concentrated in this region here. And so the charge that is concentrated in this region here is what I'm calling Q1F, and the charge that is concentrated in this region here is what we are calling Q2F. Okay? The sum of Q1F and Q2F is the same as we had before, but Q1F is not necessarily equal to Q1 initial. Okay, so to find Q1F, what I need is C1V, and to find Q2F, C2V. So the potential difference is the same everywhere, but there is more space for the charge to be found in this capacitor here because the area here is bigger. Okay? In this portion of this new big capacitor because this area here is bigger. And that's it. That's the end of this problem.